Yeah, it looks like we have a minute to spare. We'll start in a few seconds. We'll start in a half a minute or so. Yeah, it's pretty close to 9 o'clock. This week, today we'll start out in section 7.6, integration using tables of integrals. So you can use the one that's in the back of the textbook. There are other tables of integrals available if you don't have the textbook. Tomorrow we'll look at section 7.7 on approximate integration. And then on Wednesday, as well as Friday, we'll be in section 7.8 on improper integrals. So we'll go ahead and start today's section. We'll review a couple of statements first. So these 6 exercises in the textbook involve looking up or looking for a formula in the table of integrals and using it. But here's a quote from the textbook in section 7.5. Perhaps you read this. The question, can we integrate all continuous functions? And the answer is no, at least not in terms of the functions we are familiar with. One famous continuous function that doesn't have an antiderivative that we are familiar with is f of x equals e to the x squared. When you read section 7.6, this particular function is used a couple of times in the examples. So you'll want to make sure that you read about that. I guess, sorry, I think I misspoke. You'll see this in section 7.7 tomorrow. Okay, but in section 7.6, we will evaluate integrals in terms of functions we are familiar with by using a table of integrals on the reference pages at the back of the textbook. So a thing to keep in mind, this note, integrals do not often occur in exactly the form listed in a table. So consequently, we will frequently need to make a substitution or an algebraic maneuver to get an integral that matches a form in the table. Okay, so we'll do a few examples. So on this one, use the table of integrals to evaluate the following integrals. This one is the indefinite integral of e to the x divided by 4 minus e to the 2x dx. So does anyone have a suggestion on how to start this one? Okay, this is what you can do. We see e to the x and in the numerator, and we see that e to the 2x is in the denominator. So let's try the substitution u equals e to the x. And if u is equal to e to the x, then du is equal to e to the x dx. So we want to solve for dx, and we also have the substitution for e to the x. So let's make the substitution here, since we're assigning u to be e to the x. So du is equal to u times dx. And then when we solve for dx, we get dx equals du over u. Okay, so let's make our substitutions in this integral. In the numerator, we see e to the x, so let's put e there. In the denominator, instead of 4 minus e to the 2x, we write 4 minus u to the second. Because if u is equal to e to the x, u to the second is e to the x squared, which is just e to the 2x. And then we write what dx is. Dx is du divided by u. And we can simplify this integrand. In the numerator, we have a factor of u, and also in the denominator. So they cancel each other out, and we get the indefinite integral of du over 4 minus u squared. We do know how to evaluate this integral from what we've discussed this semester already. So if we didn't use a table of integrals, how would you proceed?
The natural log.
Yeah, a trig substitution. We could pick u equals 2 times sine of theta, right? Because this has the form a squared minus u squared. Okay, but we're going to look at a few entries in the integration, or in the table of integrals. So if you can see that, I guess I can slide everything up a little bit. So it looks like entry 19 is the match that we want. Entry 19 in the table of integrals, the indefinite integral of du over a squared minus u squared. So in our particular example, a squared is 4, so the value of a is 2. And then we just use the formula. So we get this is equal to 1 divided by 2 times a. The value of a is 2, so 2 times 2 is 4. So we get 1/4. And then times the natural log of the absolute value of u plus a, or u plus 2, divided by u minus a, or u minus 2, plus a constant. Okay, so that was pretty simple. We have one more step, though, in this one. Our original substitution is u equals e to the x. So we need to put u back, or replace u with e to the x in our final answer. So we get 1/4 times the natural log of the absolute value of e to the x plus 2 divided by e to the x minus 2 plus a constant. Okay, that wasn't too bad. Let's take a look at the next problem. Okay, the indefinite integral of x to the 4th divided by the square root of x to the 10th minus 2 dx. Hey, does anyone have a suggestion on how to start this one? Look in the denominator, we have the square root of x to the 10th minus 2. So perhaps with experience, you'll note, well, x to the 10th, the exponent is even, and a lot of our integral forms involve something squared, some variable squared. So if you picked u to be x to the 5th, and then the derivative of u involves, well, du would be 5x to the 4th dx, and we see x to the 4th. So all of that experience will come flooding in, and you'll at least have an idea of how to start. So let's assign u to be x to the 5th. So that means u to the 2nd will be x to the 10th. And du is 5x to the 4th dx. And our integrand has x to the 4th dx. So we won't solve for dx this time, we'll solve for x to the 4th dx since we have x to the 4th dx. So 1/5 du is equal to x to the 4th dx. And now we can substitute. So we have this factor of 1/5. I'll put that out front. So 1/5 times the indefinite integral, and then replace x to the 4th dx. Well, we have the 1/5. And let's just put du in the numerator. And then in the denominator, we have the square root of u to the 2nd minus 2. And then we'll consult the table of integrals. I know what, I'll slide it in this way. So the entry 43 is the one that we want. This entry is the indefinite integral of du over the square root of u squared minus a squared. So that's a match for this indefinite integral. And the value of a is the square root of 2. This is our u squared minus a squared. Okay, so we just follow the formula. Then we have to keep this factor of 1/5. So we multiply 1/5, and then we just use this part. So we get the natural log of the absolute value of u plus the square root of u squared minus 2 plus c. And then the last thing to do is replace u with x to the 5th. So our final result then is 1/5 times the natural log of x to the 5th plus the square root of x to the 10th minus 2 plus a constant. Yeah, that one wasn't too bad. None of them are very bad, really. Okay, let's move on to the next example. Indefinite integral of the square root of e to the 2x minus 1. So, do you have a suggestion for substitution? Oops, I shouldn't have said that. I told you what to do. Oh well. So, what substitution would you make this time? Yeah.
It kind of looks like what we did a week ago with the x will kind of be equal to a times secant of theta, except not quite the same.
Well, that's an idea. That's not what I was thinking. I'm not saying it won't work, but you can try that out. What I'm going to do, since on the inside of the square root, I have e to the 2x, that's equivalent to e to the x squared. So what I'm going to do, and you know there are sometimes alternative ways to go about evaluating an integral. So I'm going to pick u to be e to the x, so that u to the second is e to the 2x, and du is e to the x dx. And we want to solve for dx, but at the same time, we'll keep in mind that e to the x is u. I'll just go ahead and write this as u times dx. And then dx is du over u. And then we'll make substitutions, and we get the indefinite integral of the square root of u squared minus 1 times du over u. We'll write it in a more conventional way, the indefinite integral of the square root of u squared minus 1 over u du. Okay, so let's see. See if I can. Trying to avoid folding this, but I guess I'll have to fold it. So maybe somebody already found the entry. So entry 41 is a match. Here we have the indefinite integral of the square root of u squared minus a squared over u. So the value of a is 1. So since that's a lot of writing, I won't try to squeeze that in here. I'll just write that that's equal to the square root of u squared minus a squared, but a is 1, so this is the square root of u squared minus 1, and then minus a is 1, so 1 times inverse cosine of 1 over the absolute value of u. plus a constant. And then the last thing to do is replace u with e to the x, since that was our substitution. Okay, so our final answer on this one, the square root of e to the 2x minus 1 minus the inverse cosine of 1 divided by e to the x. So I'm not bothering to put absolute values around e to the x because e to the x is never negative. E to the x is, in fact, never 0. E to the x is always positive. Okay, the next example. Okay, the indefinite integral of sine of x squared cosine of x times the natural log of sine of x dx. So how would you start with this one? Yeah, we'll use substitution. We see sine of x is, we see this composition of functions, the natural log of sine of x. So perhaps an obvious substitution is u equals sine of x. And then du is, what's du? The derivative of sine of x is cosine of x, and then dx. We see that our integrand has cosine of x dx. So when we make substitutions, sine of x squared becomes u squared. And then times the natural log of u. And then cosine of x dx is du. Okay, then we consult the table of integrals. Did anyone find the entry, if you have that available? I see one person with the table of integrals. Did you find it?
Not yet. I found it.
Which one?
It is 100. Entry 100.
100?
Yes.
Oh. I'm going to use 101. I don't have 100 in front of me, so I'm not sure which one that is, but unless I made a mistake, you know. So
No,
at least
that's
when
mine.
I did it,
Would be 101.
101. Okay.
Yeah.
So we're in agreement.
Yes.
Oh. I see my problem. Okay, this is 101, if you can read it. Looks pretty thin up there. Can you read it from back there? Yeah, so this is the indefinite integral of u to the power n times the natural log of u du. So we get u to the n plus 1 divided by n plus 1 squared times the quantity n plus 1, the quantity n plus 1 times the natural log of u minus 1. Okay, so n is equal to 2. So we'll have u to the 2 plus 1, or u to the third. And then divided by 2 plus 1, 3, 3 squared. So 3 squared is 9. And then times the quantity n plus 1 is 2 plus 1, or 3, times the natural log of u minus 1, plus a constant. And then the last step, replace u with sine of x. So we get sine of x to the third over 9 times the quantity 3 times the natural log of sine of x minus 1, and then plus a constant. Okay, the next one. The indefinite integral of the square root of 4 plus the function natural log of x squared over x dx. Okay, a suggestion on how to start?
I think could you not substitute u for the natural log of x?
Yeah.
Using the derivative of that to be 1 over x to get the derivative?
Yep. That looks really small. Yeah, so since we have in the numerator of the integrand the square root of 4 plus some function of x squared, then it seems likely that we can use a substitution u equals that function, natural log of x. And then du, the derivative of the natural log of x with respect to x is 1 over x. So we get du equals 1 over x dx. And we see that we have 1 over x dx. Since we're dividing by x, that's equivalent to multiplying the numerator by 1 over x. So we're going to be able to replace the dx over x with du. I'm sure it's obvious, but I'll write this in a little more detail before I make the substitution. So this is our write this over 1 and then dx over x. 1 over x times dx is dx over x. Okay, so when we make our substitutions, we get the indefinite integral of the square root of 4 plus u squared du. We know how to evaluate this without using the table of integrals. What would we do if we didn't want to use a table of integrals? Or you can use a table of integrals.
I think we covered this last week when we did the 8 squared plus x squared, and then take the square root of that. And that equals like a times tangent of theta. Or is that a different kind of problem?
Yeah, if I understand, assigning u to be 2 tangent of theta? Yeah. If we assigned u to be 2 tangent of theta, we could proceed using the trig substitution. U equals 2 times tangent of theta. We could try that later if you want, but for now, let's just look for a formula in the table of integrals. Let's see. I'll slide this up a bit, if that helps. Yeah, it looks like entry 21 is the one that we want. The indefinite integral of the square root of a squared plus u squared du. That looks like what we have here. So that looks like a lot. Let's see. Fold this in. Okay, so we'll just fill in what the right-hand side is going to be u over 2. So times the square root of 4 plus u squared plus a is 2, so 2 squared is 4. 4 divided by 2 is 2. Times the natural log of u plus the square root of 4 plus u squared plus a constant. Yes, so that was entry 21. And then we put the natural log of x back in for u. So we get the natural log of x over 2 times the square root of 4 plus the square of the natural log of x plus 2 times the natural log of the natural log of x plus square root of 4 plus the natural log of x squared plus the constant. So if you're interested, maybe a little later we can use the trig substitution on that one and see what happens.
Professor,
What's that?
I just have a question.
Okay, go ahead.
So for the test, will we be given a table of integrals, or is that something that we will need to like study and try and memorize, or?
Well, there are only 120 formulas, so you can probably memorize those. I'm kidding, of course. Yeah, I am thinking about writing a formula sheet for you so that you won't have to memorize these big formulas like this.
Okay, thank you.
Yep. Okay, let's do the next example. Okay, the indefinite integral of arctangent of the square root of x divided by the square root of x dx. Arctangent is the same function as the inverse tangent. So it looks like an obvious substitution is u equals the square root of x, which is x to the 1/2, if that helps. And then du is 1/2 times x to the negative 1/2 dx. Which is dx over 2 times the square root of x. So in our integrand, we see that the denominator has the square root of x. So that is, we have dx over the square root of x. So we want to keep the dx over the square root of x part, and so we'll just multiply both sides by 2. So we get 2 times du equals dx over the square root of x. Okay, so I'll rewrite this integral so that it exhibits more explicitly what we need to notice. We have the integral of the arctangent of the square root of x times dx over the square root of x. So we're going to replace dx over the square root of x with 2 times du, and then replace this square root of x with u. So we'll bring the constant 2 out front, so we get 2 times the indefinite integral of the arctangent of u du. We've already found this indefinite integral a couple times this semester already, using integration by parts, but we're going to use the table. So in the table, entry number 89, okay, so there's entry 89. This is inverse tangent, but that's equivalent to arctangent. So we'll just use that formula. We have a factor of 2 to keep out front. So this is 2 times all of that. So we have u times inverse tangent of u, but I'll go ahead and write arctangent of u minus 1/2 times the natural log of 1 plus u squared plus a constant. Okay, then in the next step, we'll do 2 things at once. I'll distribute multiplication by 2 and also replace u with the square root of x. That's our original substitution. So we'll get 2 times the square root of x times the arctangent of the square root of x. And then minus 2 times 1/2 is 1, so minus the natural log of 1 plus x, because the square root of x squared is just x. Okay, the next one, the indefinite integral of, what's the name of that function in the numerator? Can you see it? It's not a typographical.
Is
It's
it hypercotangent?
hyperbolic cotangent. Yep. No, we don't see that very often. Okay, but in the numerator, we have the hyperbolic cotangent of 1 over y. So I think, well, it's my belief, I'm just surmising. I think that what the author of the textbook means by an obvious substitution is you can have 1 over y, like hyperbolic cotangent of 1 over y. An obvious substitution is u equals 1 over y, which is y to the negative 1. And so du is negative 1 times y to the negative 2 y, or negative dy over y squared. Oops. Okay, in our integrand, we see the dy over y squared. And so when we solve for dy over y squared, we just get negative du equals dy over y squared. Okay, so when we make our substitutions, we have to include the factor of negative 1. So I'll put the negative out front. And we have hyperbolic cotangent of u, and then dy over y squared is negative du. Okay, so we consult the table of integrals. Did anyone find it? So entry 106. Now the indefinite integral of the hypercotangent of u du is the natural log of the absolute value of hyperbolic sine of u. So our answer then is negative natural log of the absolute value of hyperbolic sine of u plus a constant. And then the last step, replace u with 1 over y. So we get negative natural log of the absolute value of the hyperbolic sine of 1 over y plus a constant. Okay, so I ran out of examples, but we are going to go back to that one. I'll get some scratched away. So let's just see what happens if we use a trig substitution on this one. So inside the square root, we have 4 plus u squared. So the trig substitution that goes with that is u equals 2 times tangent of theta. And du, so what's du? Telepathy? Oh. The derivative of tangent of theta is secant of theta squared. So du is 2 times secant of theta squared d theta. Let's work on the square root of 4 plus u squared on the side, and then we'll put that in later. So if u is 2 times tangent of theta, u squared is 4 times tangent of theta squared. Inside the square root, we can factor 4 out of the 2 terms. So we have the square root of 4 times the quantity 1 plus tangent of theta squared. Let's go ahead and take the square root of 4. Square root of 4 is 2. And then 1 plus tangent of theta squared. Secant of theta squared, right? So we have 2 times the square root of secant of theta squared. So this just becomes 2 times secant of theta. Okay, so we're just going to replace, in our indefinite integral, we're just going to replace the square root of 4 plus u squared with 2 times secant of theta. And du is 2 times secant of theta squared. And we get 2 times 2 is 4, so 4 times the indefinite integral of secant of theta to the third theta. So we did this in class one day, the indefinite integral of secant of theta to the third d theta. We used integration by parts to do it. But if you remember, if it kept you awake at night, you remember that it took several minutes to do it. So you can go back into your notes and see if the indefinite integral of secant of theta to the third d theta equals the answer we got using the other method. In this particular, we started out, if you remember, the original problem involved a substitution, u equals the natural log of x. So there would be quite a bit to do. I'll just mention what you would do. You would find this indefinite integral of terms of theta. Then you would write it in terms of u, because that was our intermediate substitution. And then lastly, replace u with the natural log of x. So I'll look at this and at least tell you if everything works out the way it should tomorrow. Okay, there's 3 or 4 minutes left. Tomorrow in section 7.7, we're going to start talking about approximate integration. You already know some things about approximate integration. So if you want to estimate or approximate a definite integral of a continuous function f of x on the domain interval from a to b, so the idea you have the graph of some function y equals f of x. And if you divide the interval from a to b into n subintervals, so the left endpoint a is assigned to be x sub 0, and then the next interval is the next endpoint of the subinterval is x1, then x2, and so on. other end, we have x of n minus 1 and x of n. And then if you want to get an estimate of the definite integral using areas of triangles, or sorry, areas of rectangles, one way to do it would be using the left endpoint approximation. So each one of these is a rectangle, and the base of each of those rectangles is the same delta x, which is defined to be b minus a over n. And so a left endpoint approximation of the integral, also called L sub n, that's equal to f of x sub 0 times delta x plus f of x sub 1 times delta x, and so on. Then on the right, the last term is f of x of n minus 1 times delta x. I'll just write one more thing. You've seen this before. This is an example of a Riemann sum. So in sigma notation, the left endpoint approximation is the sum from I equals 1 to n. And then the terms have the form f of x of I minus 1 times delta x. Okay, so I just threw this in there because we had time. We'll go into more detail tomorrow in section 7.7 on approximate integration. Okay, but that's all for today.
Hey, Professor.
Yes?
Did you email that table that you were using?
What?
Did you email the table that you were using for the problems today?
Oh, I don't have an electronic copy of the table of integrals. I could look for one, but it might not be the same that's in the textbook.
Okay.
I think if you go online, you can probably find a number of places that have the table of integrals there.
In the back of our textbooks.
Yeah, they're in the back of the textbook if you have a textbook.
Okay.